So question 9 says, well, find the area. Find the area of this object in the first quadrant. Question 9. Find the area in the first quadrant. Well, so as we saw, this is our graph. This is our graph, and this is like this. And because it doesn't have symmetry, well, we cannot divide this up. The theta is bounded between 0 and pi over 2. So we get 0 to pi over 2, and 0 to, what was the function? 2 times square root of 2 minus sine 2 theta. Then we have r dr d theta. So question says, hey, find the area, and your r is equal to 2 times square root of 2 minus sine 2 theta. Well, the rest is taking the integral 0 to pi over 2, and here you have a half r squared. R is bounded between 0 and 2, square root of 2 minus sine theta d theta. Then we plug in this guy here, and we start taking the integral. A half 0 pi over 2, and then here we have 4, 2 minus sine theta d theta. So you can cancel out these two, get 2 and 2 theta, and you have plus cosine theta, and theta is bounded between 0 to pi over 2. Well, here you get 2 times. If you plug in 2 times pi over 2, you get pi, and this is going to be 0. Minus, if you plug in 0, you get 0, and here you have 1 plus 1. So you get 2 times pi minus 1. This is the solution. Question 15. Question 15 says, well, what do we have here? You have a wedge, which is cut this way. We have a wedge. And the wedge is part of the cylinder. X squared plus y squared equals to 1. And the planes z equal to 0 and z equals to negative pi. And this is the graph. I'm going to flip the graph so we have a better visualization here. This is my x and this is my y. This is my x, this is my y. And if you want to just take a look at the cut of the wedge, here we have this object. This object in xy plane. In xy plane. Well, question says, well, evaluate the integral as equivalent to iterated integral. Well, we can create a triple integral using x, y, and z, or we can just use a double integral. Since we have our function here. So note that if I move this wedge, this is the behavior of the wedge that we have. So what do we have here? So if you want to focus on your x is bounded between -1 and 1. Your y is bounded between from below by negative square root of 1 minus x squared and on top by 0. So this is my y, square root of 1 minus x squared and on top by 0. And then for your z function, z is equal to 0. It means that you're dealing with x, y plane. So you have x-axis, you have y-axis, and this is the z. And then And this is your range. There we go. So z equals to, let me just graph this guy. Okay. This is my edge. And it's going on top a little bit. Not a nice graph, but still get what's going on. So z is equal to negative y, which is a plane, a tangent plane if you think about it, and then z is equal to 0. Z equal to 0 is this one here. This is your z equal to 0. When y is, for example, 1, there's your z. Z is negative 1 down here. When y is equal to negative 1, your z is positive 1. So it's going to be up here. Let me just see. Down here. Okay. This is your z and 1 here. So this is the plane. Z equals to negative. So the way that you can set this up is you can say that my z is bounded between on top negative y and down below 0. So you get the iterated integral, for example, negative y minus 0. And then here you can have your dy dx, x is bounded between negative 1 and 1, and y is bounded between negative square root of 1 minus x squared, and on top y. This is one way that you can represent this iterated integral.